Now I would like to show the execution of some other program. So that is simple program. That is, how can we perform a simple math operation by using here? What can you see? Here we are going to perform the addition of two numbers. We are going to perform the addition of two numbers with the help of a simple device. That's it. There are two numbers A and B. We are going to perform the addition of those two numbers and storing the result in C. After that, we are going to print that particular result here. We're going to print the result here, right? Okay. To do that, what we have to do? Okay. Yes. From here, we can pass these two arguments, 10 and this 15. We can pass these two arguments by using call by value. We can pass those two arguments by using call by value. After that, what are we going to do? Once we are going to perform the addition here. This is temp equal to A plus B. After that, we are storing that particular result into the third variable. Okay. This is the memory. In this case, C is a variable of type integer. C is a variable of type integer. Okay. In that particular variable, we are going to store the result. In that particular variable, we are going to store the result. Actually, for time being, instead of that particular one, we can perform the addition uh, simple with the help of simple statement, simple C statement, that is star C equal to star C plus temp. Are you with me? Are you with me? Is there any problem while understanding that? Are you able to understand this particular function? Is there any doubt?
Yes.
Okay. Next, when you look at this particular uh, prototype of this particular one, there is a keyword underscore underscore global underscore underscore. Means that this particular function is going to be called from the host. This is the host. Which one is the host? Here, this is from the main function. We are going to call that particular one. Now try to understand the main program. When you look at the main program, here what can you see? Here you can see few variables. RES. This variable is used to to print the result on the screen. Okay. Next one, RES GPU. Okay. That is, this is the variable. Suppose we are going to perform this particular computation on the device. Okay. Once we perform that particular computation, we are going to store this result in this particular variable. Where is this particular variable? This particular variable on the device. Here, how do you understand this particular one? Here we have a host computer. This is host. Some memory is associated with the host. This is the memory associated with the host. And this is a device. This is a device. Okay, some memory is associated with the device. Some memory is associated with the device. Okay. Now we have two variables. RES is with host and RES GPU with device. RES GPU is with device. Suppose whenever a thread computes that particular addition, we are going to store this particular result into this particular device and into this particular device memory. After that, what we have to do? We have to copy back that particular result into this host variable. Later, we are going to print that particular result with the help of that particular host variable. With the help of the statement is responsible to print that particular result. This statement is responsible to print that particular result. Are you with me? Are you with me?
Yes.
Yeah. Here point is, okay, we know how to allocate the memory and the host. Suppose suppose if you declare a variable int res equal to 0, that means that variable is declared uh, in the host machine. Okay. Next one is suppose if you declare int star res GPU. Okay. When you look at that particular one, what can you see? We declare the variable in the host. Okay. But what we have to do, we have to declare the memory, or we have to create the memory, or we have to create a space for that particular variable on the device. How to create a space for that particular variable on the device? To create a space for that particular variable on the device, we have to use the function CUDA malloc. Just like malloc, we are going to call CUDA malloc, okay, address of res GPU, comma, how much amount of memory are you going to allocate? We are going to allocate size of int, okay. That is, we are allocating 4 bytes of memory space for that particular res GPU with the help of CUDA malloc. So, a simple malloc function is used to allocate the memory on the host. CUDA malloc is used to allocate the memory on the device. Are you with me? Are you with me? Is there any problem while understanding CUDA malloc? Is there any problem while understanding CUDA malloc?
No, sir.
No. After that, okay, when you look at this next statement, we are calling this kernel function, that is compute using GPUs. We are going to perform this particular computation res GPU comma 10 comma 15. Okay, we perform that particular computation. After that, okay, we are going to call CUDA device synchronize. This is a simple barrier. Here, a host thread should wait for the thread which is going to be executed on the device. Okay. Later, what we have to do? Later, we have to copy back that particular result from the device to CPU, from device to host or CPU. Suppose if you don't copy back from that particular one from device to host, what will happen is we never get that particular result. Just see that particular one. Here, what I'm going to do is I would like to comment this particular one, this statement, CUDA mem copy. There is no copy here. Okay. Now I'm going to execute this particular one. Is it clear? If I commented that particular, this is more or less just like a previous one. An extra line is added. That extra line is added for that particular statement, right? That one is to allocate the memory on the device. Are you with me? Are you with me?
Yes, sir.
Yeah. Now, actually, whether are we going to compute that result on the device or not, we are going to verify it. How can we print it? We can, with the help of simple printf statement, printf result is percentage %d, comma, star c. This is the result. We are going to print it on by using that particular one. How can we compile this particular one? nvcc ex1 underscore 1 dot cu minus o ex1 underscore 1 dot o. Okay, there is no problem at all. ex1 1 dot o. Yeah, here we can see that actually result is 25. That statement is printed with the help of printf statement, which is there in the device code, right? Suppose if you going to, yeah, here I would like to add for more clarity, result GPU. Okay, here CPU. Now I'm going to execute it. Yeah, now you can see that GPU result is 225 and CPU result is 0. What is the reason for that? What is the reason for that?
CPU and GPU memory copy not happened.
Yeah. Actually, with the help of this particular simple function, we are performing that particular computation, addition of two numbers. Okay, but result is not copied back to the host. To copy back the result to the host, we have to use the function CUDA memcopy. When we look at the CUDA memcopy, here you can see that particular one. here you can see 4 arguments. For that particular function, we are going to pass 4 arguments. Okay, res variable and res GPU. That means we are copying the result from this res GPU to this variable. Okay, how much amount of data we have to copy? We have to copy 4 bytes. We have to copy 4 bytes, right? That is size of int. Next one, direction of the copy. Direction of the copy is CUDA memcopy device to host. Suppose if CUDA memcopy host to device means, then we are copying the data host to the device. Are you with me? Are you with me?
Yes, sir.
Okay. Suppose if we use this particular one, if we use this particular statement, now I'm going to, I remove that particular comment and I'm going to execute it this particular one more time. When I execute this particular one more time, now you can see that result, right? A result that is arithmetic operation that is computed with the help of kernel function. That means function that is executed on the device. Okay, we can see that particular result on the host. Are you with me? Are you with me?
Yes, sir.
Yeah. Next, here I would like to add few modifications to the existing code. Those modifications are, here we perform the addition with the help of one thread. Now I'm going to launch 4 threads. Okay, number of blocks is 1. Okay, and number of threads per block is 4. Now I'm going to, what is the expected answer now? What are you expected now? If I call that particular compute using GPUs with the help of 4 threads, that means 1 block and 4 threads per block, then what is the expected answer? We expect that uh, 25 is going to be added 4 times, right? That means we expect the expected output of that this particular program is 100. Now we are going to execute this particular one. When we execute this particular one, we can see that we actually that result is computed 4 times, but each and every time we can see that actually 25 is printed. Each and every time 25 is printed, right? And CPU results are the 25. That means there is a problem. What is the problem? Update operations of one thread, update operations of one thread are not visible to the other threads. That is the problem. Did you get my point? What is the problem here? When you are working with multiple threads, then there is a problem of data race, right? Are you with me?
Yes, sir. Yes.
How can we avoid that particular data race problem? We can avoid the data race problem with the help of atomic primitives, right? What are those primitives? Actually, here this particular statement is, instead of considering this particular one, C equal to C, there is an atomic statement that is atomic add. Atomic add. Okay, we are going to pass 2 arguments, that is C is the result, and temp. Okay, this is, now we are going to print this. Actually, now we are going to execute this particular one. See what is going to be happen. See, result is 100 now. Are you with me?
Yes, sir.
Is there any doubt? Is it clear? If you have any doubt, please let me know.
Sir, I am trying to run the same program in my machine,
Okay.
but the result is not coming actually. Display program is executing, but the result is
No,
not coming.
here what you have to do, you have to put CUDA device synchronize after compute using GPUs, right? Did you put this particular one?
Yes, sir.
Okay. Next one, you have to consider CUDA memcopy, right?
Oh, mem copy I didn't use. So that is the
Yeah,
Hello World program only.
yeah, no, no. After that, you have to copy that memcopy, right? CUDA memcopy.
Okay, 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 sir. I will try.
Okay, that is the case.
Okay, okay.
Are you with me?
Yes, sir. Yes.
Okay. Now, if we execute this particular one, now you can see that 100 is on the screen, right? Are you with me? Now? I would like to give one more. I would like to show one more statement program. When we look at this particular one here, what is this one? We are going to compute a plus b. We are going to compute a plus b. We are going to compute that particular a plus b uh, with the help of three blocks and four threads per block. Three blocks and four threads per block. Okay. Did you see my, actually, did you see this particular one? Logic is same. Here I added some other extra statements. What are the statements? Here you can see one statement that is CUDA error underscore t. Okay. That is the return type of variable CUDA status. Okay. Suppose we are allocating the memory with the help of CUDA MLR. When we allocate the memory with the help of CUDA MLR, okay, if there is any problem during that particular memory allocation, that status is going to be stored in the variable CUDA status. That status is going to be stored in the variable CUDA status. If CUDA status is 0, then there is no problem. If CUDA status is not equal to 0, then there is some problem in that particular memory allocation. Then there is some problem in that particular memory allocation. Okay. After that, return from that. Next, here, when we look at this particular CUDA mem copy, here, what are we going to do? We are going to perform this particular one, CUDA mem copy, res GPU, res and size, and this particular one, CUDA mem copy, right? CUDA mem copy host to device. That means here we are going to copy the data from host to the device. That means suppose in the earlier program by this particular res GPU with 0. When we initialize res GPU with 0, there is no need to pass it. By default, when we use CUDA malloc, default value is 0. Suppose if that should not be the case, okay, suppose if you want to initialize this particular res GPU with some value, in that context, how can we do that? In that context, how can we do that? We have to use this particular one. Suppose here, uh, I'm going to initialize. Actually, suppose if there is no, if we don't consider the statement, if we don't consider the statement, then it is just like previous one. This is just like previous one. Okay, 1 comma 4. Here arguments are 1 comma 10 comma 15. Okay. Now we are going to execute this particular one. This one is nvcc minus o ex1 underscore 2 dot o dot ex1 underscore 2 dot o. Yeah, CUDA status is 0, result is 100. That is fine. But actually, but you want to initialize some this res GPU with 50. Okay. Suppose if that is the case, when we perform this particular addition, okay, 4 times, what is the expected output? Expected output is 150. Expected output is 150. Okay. Sorry. Initial res value is 50. After that, we are going to add that particular one 4 times. In that context, expected output is 150. But we here when we execute it, we got the same output. What is the problem? Here problem is we haven't passed this particular previous result, initial result to the res GPU. To pass the initial result to the res GPU, what we have to do is before going to perform that particular computation, we have to use this function, this CUDA memcopy. Okay, CUDA mem copy. Here, what is the first one? First one is the destination. What is the destination? RES GPU is the destination. What is second one? Second one is the source. What is third argument? Third argument is the size of the memory. How many bytes of the data we are going to copy from the source. Next, what is the fourth one? Fourth one is the direction of the copy. Direction of the copy is from host to the device. Are you with me? Here you can see these four arguments. First one is the destination. Second one is the source. Third one is the size. And fourth one is the direction. Are you able to see Are you able to see that?
Yes, sir.
Okay. Now I'm going to execute this particular piece of code. When I execute this particular piece of code, what can you see? Now you can see the result 150. We can overcome this particular problem. When you look at this previous program and this program, what can you see? Okay, yeah, actually, suppose without that particular one, here we are copying some data from host to device. Later on the device, we are performing some computation. After performing that particular computation, we are copying back that particular data result from the device to the host, from the device to the host. That is why here we consider two functions. This is a function name is same, CUDA mem copy. Here also function name is same, but direction of the copy is different. Here, when we look at this particular one, here direction of the copy is host to device. Here, direction of the copy is device to host. We had to take care of that particular one. Why do we need CUDA mem copy? Suppose if we want to perform addition of two matrices, addition of two matrices. First of all, we had to copy those two matrices from the host to device. Okay, after that, by using multiple threads or by using many number of threads which are there in the device, we can perform that particular computation. Later, we had to copy back the resultant matrix from the device to host, right? Device to host. Did you get my point? Okay. Suppose anything. Suppose if you want to work with multiplication or addition of matrices. Okay, where are those matrices? Initially, these two matrices are on the host. Okay, what we have to do by with the help of CUDA mem copy, we have to copy these two matrices from host to the device. Once we copy this from host to device, we have to perform some computation. We have to perform some computation. Later, we have to copy back from the device to host. Device to host. For that, we need these two functions, CUDA mem copy, CUDA mem copy. After that, you can see one more function that is CUDA free. Okay, we are going to free this memory that is allocated on the device with the help of CUDA free, just like a free function call in C. Are you with me? Are you with me?
Yes, sir.
Okay. In this class, okay, exactly I executed two programs. Executed two programs. First one is hello welcome program. Okay. Second one is this is simple arithmetic operations on the device. Okay. In this particular simple arithmetic operations, suppose if you want to perform simple arithmetic operation, what we have to do? We are going to copy the results from the host to device. After that, we are performing the required computation. Later, we are copying back the result from the device to the host. Is it clear? Is it clear?
Yes, sir.
Yeah. Here, when we look at this particular kernel function call, we are passing 10, 15 as arguments. Suppose if you want to pass these two are also in terms of variables, then also we have to copy those two variables from device to the from host to the device. Here 10, 15, these two are declared in the function call itself. Then these two values are passed from call by value. Suppose if you want to declare those two values on the host and we have to pass it from that, okay, then we can make use of this particular simple one, right? Okay, what can I do is, okay, today I would like to share these three programs with you. Okay, hello world and this ex1 underscore 1 and ex2 underscore 2. Okay, before coming to the next class, okay, Try to execute these three programs. Okay, if there are, do you have any doubts? I would like to clarify all your doubts in the next class. In the next class, I would like to discuss how to perform the vector addition and vector or dot product of two vectors, and addition of two matrices and multiplication of two matrices. Is that okay for you? Is that okay for you?
Yes, sir.
Yes, sir. Okay.
Yeah. Thank you. Thanks a lot. Do you have any doubts?